This is note card 32. Now we're kind of talking about local extrema on an interval. And another word for local extrema is the word relative extrema. All right. So let's see what the note card says. It says, let C be an interior point of the domain of the function f. Then f of c, which means the y value at c, is a local or relative maximum if the y values, if all the y values of f of x are less than the y values at c for all x in some open interval containing c. And it's a local minimum if all the y values are bigger than that particular y value for all of x in some open interval containing c. So I know that's kind of complicated to read, so let me kind of just draw a picture and help you out a little bit. All right, so if we have some function, that looks like that. Obviously, this goes on forever. It keeps going up and up and up to the right, and it keeps going down and down and down to the left. However, at this particular point, if we focus in on numbers that are close to this x value, so if that x value is c, for instance, okay, if you narrow your focus in to numbers that are around there, okay, and do an open interval, this is a high point. So that's why we call it a relative min, or excuse me, a relative max, excuse me. A relative or a local max. It's a relative high point over a small interval. And just like that, if this other c, I'll call it C2 here, and I'll call this first one C1. Again, if you narrow your focus in on x values that are close to C2, this is the low point. Okay, if we start there and end there, there's nothing lower around that. So this would be the relative minimum or local minimum. Okay, I like the word relative a little bit more than local. Because relative means, well, it's relative because this is a high point and numbers close to it, but outside of that, the graph can still go higher. So that's why we call it it's relative. Some people like to use the word local, meaning local being close to that x value, but I like the word relative. Okay, and just like here, if we kind of narrow in our focus, the graph from here to here, there's no other y values that are lower, but if we expand our view, we can get lower somewhere else. Okay. So that's why those things are called relative maxes and mins. So let's do a couple problems here. It's a relatively short note card. So it says, using the graphs of the following functions, determine the relative or local maximum values and the relative or local minimum values. Okay, so the first one, they're asking us to use our calculator to do. So I've actually already put this function into y1 right there. I put the other two into y2 and y3. I just turned them off. Okay, so let me just do zoom standard. Okay, so if I start to look at the graph, okay, what we're really looking for is we're looking for the humps and the valleys in the graph. Okay, the relative high points and the relative low points. To me, this right there, about right there, looks like, you know, relative to numbers around it, it looks like that's a minimum right there. And we can actually figure out where that minimum is going to be. Okay, so if I hit second and trace, there's an option that says minimum. So I'm going to select that one. Now it's saying, okay, what's your left bound? So pick a point to the left of where you think the minimum is, and just hit enter. And then pick a point to the right of where you think the minimum is. Okay, and then it says guess. So I'm going to kind of look at these y values and I'm going to say, okay, which one's the most negative? Okay, so maybe about right there. And I'm going to hit enter again. Okay. And here it tells me that the minimum occurs at that point. Okay, at -3, this is about -3, -2. All right, so I just found the local min is at the point -3, -2. So what does that actually mean? That means that the relative minimum value is actually the y value. Okay, the relative minimum value, that's the y value, is -2, which occurs at an x value of -3. Okay, which occurs at an x value of -3. So the actual value of the minimum is -2, and that occurs at that x value of -3. Now, what about the relative or local maximum? Okay, if I focus in about right there and that high point in the graph, that looks like where the relative maximum is. It doesn't look like there's anything higher around it. Okay, now over here it does go up to infinity, but I'm just looking at numbers that are close to right there. So if I go second trace, I can find the maximum, which is option 4. Okay, so it says left bound, so I'm going to keep scrolling over and come close to the maximum on the left side, hit enter, and come close to the maximum on the right side, hit enter. And it says guess. So I think that's probably where the maximum is. And if you notice the maximum here, it tells me that occurs at 3, 2. Okay. So the point 3.2 is where that's where the max is. So the relative maximum value is 2, which occurs at an x value of +3. Let's try the next one. Now you should know what that graph looks like. Y equals the absolute value of x. Okay. You should know that parent function looks like a V. And it goes on forever in that way. Okay. So if I want to think about this point right here, it never goes lower than. Okay. So this is not only a relative min, it's also an absolute min. Okay, so B, the relative min equals, what's this point? It's the point 0, 0. So the y value is 0. The relative min is 0, which occurs at an x value of 0 as well. Now let's think about relative maxes here. There's no humps in the graph. There's no relative high points in the graph. All right, if I think here, there's something close to it that's bigger. I think here, there's something close to it that's bigger. So there's no relative maxes in this graph. There's no relative maximums. And number 3, they ask us to use our calculator. We want to look at this graph, or this function, this trig function, over this interval, just between -10 and 10. So on my calculator, I already put that into y3, and I am in radian mode, which I have to be. Okay, so x plus 3/2 sine of x. And I'm going to just change my window from -10 to 10. And then I'm going to use zoom 0 or zoom fit to help me out. Okay, so that's what the graph looks like. over the course of x values between -10 and +10. So to me, the relative mins are all the relative low points in the graph. Okay, so let's list these out. And the relative maximums are all the relative high points in the graph. Okay, so to me it looks like there's 1, 2, 3 relative high points, and there's 1, 2, 3 relative low points. So we'll find the maximums first. Okay, so we'll find the relative maximums first. So here, I'm just going to go second, calculate, number 4, maximum. And we know we're calculating a maximum because up at the top of our screen it says calculate the maximum. So that one right here, this high point in the graph, looks like the first relative maximum. It says left bound, right bound, so pick a number, pick a point to the left and the right that bound the max, and then guess. Okay, so this first one, the first relative maximum, that's a relative high point right there. Okay, so the first relative maximum has a y value of -2.865 if I round, at an x value of -3.983. So this is the y value is the actual value of the maximum, and it occurs there. In a similar manner, we just do the same thing again. Second calculate, let's calculate the next maximum. So this is the next relative high point in the graph, about right there. So it says left bound, right bound, guess. So there's the maximum value, 3.419, and that's where it occurs at that x value. So 3.419, and that occurs at an x value of 2.301 if I round to 3 places. Okay, so there can be more than one relative maximum. There can be many relative maximums. We're going to find this last one real quick, the last relative maximum. It says left bound, right bound, guess. So that's the last value. The y value at that one is 9.702. And that occurs at an x value of 8.584. Now, relative mins mean the relative low points. So in here, we would be talking about that low value, this low value, and that low value. So we'll go second, calculate, and we'll go to minimum. And there is a calculus way we're going to find these. Okay, you might already know what that is, because you know at those relative minimums, the derivatives would equal 0. So, all right. So in the same way, calculate the minimum. Left bound, pick a number to the left of the minimum. Right bound, pick a number to the right of the minimum, and guess, pick where you think the minimum is. There we go. That's the first relative minimum, the y value there. So the first relative minimum is -9.701, and that occurs at an x value, well 702 if I round, sorry, at an x value of -8.584. Now we're going to find the next one, second calculate, the minimum. Okay, we're going to go near the next low point. There's the next low point, the valley. Left bound, right bound, guess. Okay. So the y value there is -3.419. Okay, and that occurs at an x value of -2.301. Okay. one more time. Let's calculate the last minimum, the last low point in the graph. Right there. So the left bound, right bound, yes. Okay, there it is. So the y value there is positive 2.865. That occurs at an x value of 3.983. And what you'll notice, this curve, okay, think about this curve. All of these just happen to be the positive versions of these, okay? Like they're the opposite signs, and here the signs are opposite. That's not a coincidence for this particular function. Okay. This function happens to be an odd function, and that's why that happens. Okay. So that's the note card. So the big takeaway, relative maxes and mins, okay, they're like the humps in the graph. Okay. And it doesn't even necessarily have to be a hump. It can just be kind of like a hard corner. Okay. So like that's a relative max. Okay. That's a relative max. This would be a relative min. Okay. So they're the humps in the graph. That's the way I like to think about it. Now your packet for this particular for this particular note card, packet 32, kind of modifying some of this. So here it says, the figure on the right, in the interval, the closed interval between -1 and 8, it's asking you about absolute maximums and minimums and relative maximums and minimums. Okay, so let's do this one together. So it has an absolute maximum, which means the highest point. Okay, what's the biggest y value? It's 12. That's the value. Or wait, it says at, excuse me. So the maximum happens at an x value of 8, and the absolute maximum value is 12. All right, f has an absolute minimum at an x value of -1, and the actual absolute minimum value is -2. All right, relative maximum, that's a relative maximum right there. Okay, so that occurs at an x value of 2, and the value there is 9. Has a relative minimum at an x value of 5, and the value of the minimum is 3. So that's how we would do that problem. Okay, now if you look at the next couple, it's asking you about absolute maxes and mins and the values. Okay, so if you think about this curve, all right, it might not have an absolute, might not have a certain thing. So here, this is an open circle, so it does not meet the requirements of the extreme value theorem. Okay, so there is no absolute max. We get really close to a y value of 5, but we don't ever actually get there. All right, so the absolute max does not exist. Okay. Okay, so I'd write DNE there. But it does have a minimum. Okay, the absolute minimum value, it never goes below a y value of 1, and that occurs at 2. All right. If we think about the next one, think about this curve. Do we get to a high point? Well, we get close to a y value of 5 there, but because of the non-continuity, okay, because the function's not continuous, we don't actually ever get to the high point of 5. So we don't have a max again. We do have a minimum though, okay? We get to a minimum value of -1 at an x value of -1. And number 4, okay, this is a filled in circle. We do get a high point out of this graph. So the absolute maximum value is 2, and that happens at an x value of 3. Okay. Now, do we have a minimum value? Here you got an open circle, and here you have another open circle. Okay, so we get close to y values of -1, but we don't ever actually get there. So this one does not have an absolute minimum. And what conditions are necessary to guarantee that there will be an absolute max and an absolute min? So we need the function to be continuous on a closed interval, a to b. That's what we need. Function has to be continuous, and you have to have filled in circles on the endpoints. Okay. So this one violates the closed interval purpose. This one violates the continuity piece. And this one violates the closed interval. And that's why we see D and E's, and part of the answer is there. Okay. So do the rest of this page real quick. And then on the back, you have some multiple choice questions. Make sure you show your work and talk about your rationale to get full credit. And that's going to do it for this note card.